Okay, so we'll start with our second to last look at the calendar. Today is the second to last class day of the semester. We just took our last quiz. Today we talk a little bit about parabolas and just a general overview of the conic sections, the 4 different curves we've been talking about. One nice thing I think about today's class is that there's really not a whole lot that's testable from today's class. This is just kind of a gentle conclusion to thinking about these conic sections. So pretty much we've covered like the hardcore, like testable material that you're going to see on the final exam, and we'll just kind of, take it easy as we stroll through some of the, reasons for thinking about conic sections, but nothing too intense today. On Monday is our review day for the final exam. I have no agenda for Monday other than to give you just like 5 minutes of general stuff about the final exam, but then for the most part, just we're going to be working in groups on whatever we'd like to be working on, maybe making the reference sheets for that test. Just one note, and we'll say this again on Monday, you're allowed to bring in 3 pieces of reference material for that test. So if you have been holding on to the reference sheets for the first 3 tests, bring them back in and just add a little bit of stuff for the conic sections. And then Friday, 1 week from today, this course will be done when we take our final exam. Note the exam starts at 10:30, although we'll probably change that time to 10 o'clock or something. Yes? So is it 3 pieces of paper plus? It's okay. I don't want to commit to anything before I look at what I wrote. So let's look at what I wrote. Okay, so on the last page of the test, on the last page of the packet, I wrote, you can find it here. Let's see. Okay, 3 one-page sheets of notes, unit circle, trig identities, and the conic sections formula sheet, which I don't even think we've mentioned, but it's the very first page of this packet. Is that right? No. 3 single pages, front and back. Front and back. Bring in your 3 notes from the first test. All right, so a couple of things to talk about before we jump back to this page here, which again is 62. So first, at the end of this semester, the Math Studio is having a pizza party. It is free, so come and get some pizza. It'll be right after our class on Monday at noon in the studio, okay? Next, the last day for normal studio coverage, that is when the faculty are on duty for drop-in hours, is Monday. So we will be there as scheduled for this coming Monday. That's the yellow schedule that you guys will see all over the place. But once Monday ends, the yellow schedule is no longer it's no longer applicable. So for the rest of the week, Tuesday through Friday, there is a blue schedule, which you will see posted here and in the other math classrooms and in the studio. I'm not going to make copies of this for everybody. Just come on up and take a look at it and figure out when you'd like to come in if you want. The coverage is not as much as during the week. There just aren't as many tests on the end of the week, and so there's not as much coverage as you can see from the gap over here. If you do end up coming in on any of those 4 days, Tuesday through Friday of next week, and somebody is there helping out, then thank them because they are there voluntarily. I cover the studio right now. I am paid. It's part of my job to do that, but none of us is getting paid for Tuesday through Friday, so just thank whoever you are working with next week. Okay, so that's that. Any questions about the studio coverage? Okay, and then finally, some folks have been asking for blank copies of all of the quizzes, all of the previous quizzes, so I'm happy to provide that. I can print things out today and bring it in on Monday. I just need a sense of how many people would like a blank every single quiz we've had. Don't be shy, it's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I will make 11 copies of all of the quizzes. And I'll bring them in on Monday. Okay, so let's start talking a little bit about the conic section stuff here. So we'll begin with number 1, Ernie. So you guys have been playing recently with equations for these conic sections, like x squared over 9 minus y squared over 16 equals 1. What is the name of the graph of that equation? That's a hyperbola because of the minus sign. So you've been looking at equations, but that was not how these shapes were originally thought of. It was all geometrical like you guys did outside. We'll go to Vanessa for 2. Okay, Hillary for 3. Okay, so for example, and we saw this picture before, if you add blue and blue, that is you walk from the focus to a point on the ellipse to the other focus, compared to adding purple plus purple, what will happen? It'll be the same. Doesn't matter how you walk, you will always walk the same amount if you go from focus to ellipse to focus. That is how you get to be on the ellipse, is you are one of those magical points that it's the same walk all the time. Okay, let's go to Garrett for here are. Okay, so if we were to throw some axes, x and y axes right through the middle here, so that the center of this ellipse really is at the origin, and the two foci now are on the x-axis, then it turns out that that there's a way to figure out where those foci are based on the a and the b in the equation. So for example, if I give you this ellipse, let's say it's x squared over, this one's a little bit longer on the horizontal, so we'll do x squared over 25 plus y squared over 9 equals 1. So what is the left-right distance from the center to the ellipse? It's 5, right? That's the a squared is that number. So out here we got a -5. Over here it's a +5. How about the up-down distance? That's a 3. So 3 there, -3 there. But one thing we haven't talked about until now is where are those foci? I mean, they exist. They're someplace for that ellipse. Can we figure out exactly where they live other than just saying roughly they're someplace on the x-axis? So it turns out that what most people do is they give a letter. The letter we give is C for the distance between the center and the focus, which means going the other way, it's also C. It's the center is right in the middle. So C is going to be our letter for how far you got to go from the center of the ellipse to get to one focus, either way. And it turns out there's a nifty little formula that tells you how to find C for an ellipse. It's square root of a squared minus b squared. So for this example, square root of, how much is a squared? It's actually 25. Remember, a squared is really just that number sitting down there. So 25, subtract b squared, subtract 9, and we get the square root of 16, which is 4. We'll just say C is positive. So what does that mean? That means that the one focus is out here at 4, 0, and the other focus is over there at -4, 0. Questions on that?
Yeah, why is it so similar to the Pythagorean
theorem? Yeah, it's a good question. Topher actually kind of figured out the other day, not verified, he created that formula without really knowing that it existed. Topher, did you use the Pythagorean theorem when you were doing your thing?
Well, yeah, because two foci, two and so
I have to refresh my memory because I don't remember your picture. Was it from here to the focus? Okay, so oh, it's the blue.
So I didn't even know. I made basically 2C. And so
Can we pause for 1 second, Topher? So I saw your picture and I saw exactly what you did, and I'm a little bit lost with just the letters floating around right now. But roughly, it was a couple of Pythagorean theorem stuff. So potentially, I mean, he used it in getting that formula. Yeah, so we'll say that. And okay, so that's fine. And this is if the A is the bigger one. If the B is the bigger one, then just make that one, like subtract the other order. You just have to make something positive inside of the square root. So that's where the foci are. And we'll go ahead and take a look at a Java applet. You have the link there, so you can look at it on your own if you'd like. But if we take a look at this one here, so here's our ellipse, and all of the orange things are movable. So for example, at this moment right here, A is the length from one focus to this random point on the ellipse, and it is red, and it is the length of this line segment here. And if we go from that same point to the other focus, it's B, it's blue, and it's that. Now what's going to happen if I take this guy right here and I move it, say, up and left? What happens to red? It gets shorter. What happens to blue? It gets longer, bigger. But do they have something to do with each other? Better be exactly the same, right? However much shorter A gets, B has to get longer by the same amount because we need the total walk to always be the same. So this line segment is going to look a little bit different, but it's still the same total length. And no matter where you are on this ellipse, if you walk and then walk, it's always the same. It's always this distance here, A plus B. And one thing that that maybe some of us thought about when we were outside, if I move to this point, it's still true that I can walk from the one focus straight left and then all the way to the right, and it's still the same distance. Well, what is that distance? Let's see. The red distance right now is just from this focus straight to the left. The blue distance is from here to here. So I kind of feel like I've double counted this piece in here, like blue and red are both on top of each other. So what if I just kind of take that part of the blue and shift it over into this lonely empty space over here? So then do you believe that blue plus red is really just the distance from here all the way across to there? And in fact, you can even see it now looking at that line segment. It's perfectly lined up with both ends of the ellipse. So you can tell how far you're going to walk. It's that straight line distance the long way. And you can move other stuff too. I can move the foci. Do you guys remember what happened outside when you moved the foci closer to each other? It became more like a circle. That's right. So if I take this guy and move it closer and closer, closer, more like a circle to a point where, oh look, it's a circle. I forgot that it did that. I was pleasantly surprised when it did that. Yeah, to the point where it becomes exactly a circle. So a circle does have one center, but you could think of it as having two foci. They happen to be exactly the same point. Yeah, so that's that. Right. Okay, good. Let's come back here and.
So, I'm just like using C, like the equation using for C squared.
Yes?
It's confusing because C isn't the longest side.
Yes, so that's why I don't know.
If we're normally solving, let's say B, have square, so the square root of the square, really in this square.
I think there's a connection in there. I don't have a in my. Well, we're going to come down to a new equation down here, which is going to be, that one really looks like Pythagorean theorem to me, like the right letters in the right order, just square both sides and you've got your Pythagorean theorem. But these two equations are quite different, right? You subtract the a squared minus b squared versus down here you add them. So, so there is Pythagorean theorem stuff going on. I think it's just sort of a coincidence of the lettering that we want to see it as being, oh, that's just the Pythagorean theorem. Okay, so let's move on to 4 and Chris. Okay, so let's take a look at that one. Although in fact, let's first take a look at something else. So Tassiday brought in a book the other day. Where can we go? Here. And I'm going to project a little part of this book. So first the cover. This book is called Math Equals, Biographies of Women Mathematicians and Related Activities. We're going to jump ahead to page 23. And this section of the book is about the earliest known female mathematician. Her name was Hypatia. She lived in she was an ancient Greek. I don't remember her exact dates, like 200 AD. What is it? No, not that late. Really? Does it give? it must give her time, right? Hypatia. There we go. Here maybe? Is that right? No, that's Alexander's death. Hypatia was born 370 AD. Okay. All right, so we'll split the difference between. All right, so here's something Hypatia did. Now remember, Hypatia did not have the benefit of axes and coordinate geometry and x's and y's and all that jazz. So it was really like entirely geometrical. And so here's how she thought about creating an ellipse. You guys made ellipses outside with string and just 2 points and some chalk. And so here's what she did. She took I don't know if I can write on this. Oh, I can. So she took her two foci, so there's the two foci right there, and then she started making circles. And she made the circles in such a way that, for example, this smallest circle, the one labeled a 1, we're going to call that 1 inch, so 1 inch. And then the one labeled a 2 is 2 inches. So these aren't just random circles. They are exactly 1 inch in radius and exactly 2 inches in radius, and keep going bigger, bigger, bigger. And so let's take a look at a point on the ellipse. For example, this point right here. Somehow she's come up with that point is on the ellipse. So we're going to walk. There to there is blue, and here to the other guy is green. Now, that point, by being blue, is on which numbered circle? Can you tell? That's 3. So how far is it between the focus and the blue? It's 3 because it's on the circle of radius 3. Now, blue is on another circle, a really big circle, which it looks like it's the 6th one here. So how long is green? 6, by virtue of being on that circle. So how long is the total walk, blue plus green, is 9. So that's one point that's on the ellipse. But if you want a different point on the ellipse, for example, we could take, say, this point right here. Which 2 circles have we picked? Well, you just need to pick 2 that add up to what? 9. So for example, how much is that? That's a 2. So then the rest of it, that better be a 7. Which it is. So just pick a bunch of things that add up to 9 and you've got an ellipse. And a really, really nice thing about this is that it didn't have to be 9. We could have picked 10 and we'd get a bigger ellipse. And for example, I could pick, let's see. So if I want 10, then maybe I can take my 7 circle and mush it with a 3 circle. So here's my 3 circle coming around. Here's my 7 circle coming around. There is a point on a bigger ellipse, the 10 ellipse, instead of the 9 ellipse that's drawn. So you got a whole family of ellipses here. You just have to put the dots in the right spots. Really clever. Okay, let's come back, close, and here. Okay, so sorry, Chris, again with the hyperbola. Oh, can you, I'm sorry, could you read the definition again?
Oh, yeah. A hyperbola is
Okay, so same idea. We're making walks between the one focus and some random point on the hyperbola, and then from that same random point to the other focus. But this time, what's supposed to be true is not red plus purple as a constant, but the difference, purple minus red, is supposed to be a constant. So if you picked a different point, say this guy over here, red is a little bit shorter, but so is purple. And they're both supposed to be shorter by exactly the same amount. So when you subtract them, you get the same number every time. So the foci here, there's a formula for finding them. If you know your A and your B, it's the same. That's an equation of a hyperbola at the top. A is 3, B is 16, sorry, B is 4. And if you want to figure out exactly where the foci are, it's that equation. Almost identical to the ellipse one, just a plus sign in the middle. I'm not going to quiz or test you on it, but the way that I would remember which one went with which was that the ellipse has what in the actual equation of the ellipse? has a plus, and in the focused version of it, it has a minus. And the hyperbola has a what? Has a minus, but in the focused version, it's plus. So I would just remember they were opposite. Okay, another applet for hyperbola. So let's take a look at this guy. All right, so I think we can close stuff as we go. What is happening here? That's for later. This one here, parabola. Somebody help me out. Where's the one I want? That one? Focus. Sorry, thought I had them all open here. IES hyperbola. Is it that one? No. That one? That one? Yes. Yes?
Yeah.
Wait, is that really? Is that really the one? Yeah, but that's not the one. It's not that one either. Sorry. I could. It's not a live link in Smart Notebook. IES. Okay, so where is it? Draw hyperbola. That one? Okay. Okay. So let's take a look at this one. So somehow this guy, if I drag this thing, is going to make us part of a hyperbola. And I always have to think really hard about why that's true. So in theory, all right, so what are the two blue dots? Those are the foci. So I've got two blue are the foci. And the idea is that if you walk from this one point on the red hyperbola to the one focus, and you subtract the same walk, but to the other focus, you should get the same number every time we subtract. All right. So what's going on here? So if we move like to one of these extremes, something like out here, I can never remember like how this is supposed to work. So I've got the one distance. I've got this distance here. All right. So we've got my blue distance there, and the other walk I'll make in black is that one. And I'm supposed to see somehow that if I subtract them, I always get the same thing. Anybody see that? Distance from what to is the same? The distance from the two. Okay, so we're subtracting those two guys as vectors, and we get something between the dots. But does that have something to do with like the actual hyperbola? Let's see. So then if I move this way, I don't know. Anybody see it? It's a different walk now, so I think I did blue and black before. Garrett, can you come up and?
The idea is that as the black distance gets longer, the blue distance is also the amount they each get longer is fixed.
And where is that amount in this picture? Do you see it from that crazy device?
Well, if you drag the device, so it's perfectly. And that distance.
So where's the difference? You're saying it's the distance between the.
I think the best started probably they increase by the exact same amount.
Okay, so I feel like there's an increasing by the same amount happening just because there's however much yellow string we have in this thing. It doesn't change. So I feel like that's important. Yeah, maybe the difference that we're talking about is that space between the blue dot over there and the that point on the hyperbola. Is that it? So if I'm going to make my two walks again. So I'm making a walk here in blue from the focus to the hyperbola, and then the other walk in black.
No, it'd be a little less.
No, it is less. So I need to subtract those two, and it's. Yeah, that's what we want to see. So whatever the difference is between black and blue, it's always the same as we move along this thing. Can you guys see this any better than I can? I always have trouble with this one. So this one is getting longer by a certain amount, and this one is getting longer by the same amount. Yeah, I guess that's true, right? Because it's just the yellow string is just kind of leaving this device.
Well, and the two asymptotes that follow are straight lines, so that would make sense that it would be linear.
Yeah. I don't know. Anything else to say about this one? I don't know. Okay, so that one I have the hardest time seeing. Let's take a look at Hypatia's take on this one. So here is how she thought we should be drawing hyperbolas. So you can see the hyperbolas are the black curved things. They're drawn in there. And let's go ahead and just take a look at this point that's highlighted here. You've got your two foci. Oops. We got our two foci. And we're going to take a walk from the one point on the hyperbola to one focus, and a walk from that same point to the other focus. Okay, how long is blue by virtue of blue being on a circle? On the blue circle. I don't see 5. I think it's 6. If you follow the blue circle around, oh, that's a red circle. But if we follow the blue circle around, we land on the 6. So the blue is 6. If you follow the red circle, or just look at the number, how far is red? That's 3. Okay, so blue is 6, and red is 3. So what is the magic difference when we subtract? It's 3.
Oh, it's the exact distance. Wait. Yeah.
It is. We didn't have that picture. We didn't have that in our picture. Maybe that's why I was having trouble finding the distance that we wanted. So a couple of folks are hypothesizing that maybe the magic difference, you know, like when you subtract 6 minus 3 is going to be that. Yeah, we make our rectangle and let's see, so a sheet and draw the asymptotes. That's true. Okay, so this is an open question. Is 3 a coincidence, or is that really how you find the magic difference between the two? But I'm still not convinced that it's always 3. It's 6 minus. No, but like in this for this hyperbola, it's a 6 minus 3 is 3. Let's make sure it really is 3 for some other point. So how about we pick this point way out here? So in theory, I'm supposed to be able to make my 2 walks and subtract and get the same 3, 6 minus 3 that I got before. Okay, let's draw red. How many circles is that for red? That is 8. You kind of have to swing that circle all the way around. Instead, all right, so that's an 8. And then let's also draw in blue, which is to the other. Is that one 11? Okay, yeah, 9 circle, your 10 circle, your 11 circle is that one there. 11 minus 8 is 3. Always 3, because you're picking the right circles. You're picking circles that differ by 3. Really, really clever way to draw a hyperbola. So then I think just like there were many ellipses on the other picture that weren't drawn, I think there are many hyperbolas here. You just have to find other ones. Just make sure that you're picking circles that differ by the same magic number. So for example, if I want my magic number to be 2, then I might take like the 7 circle for the one. And what's the other circle I could pick? Maybe the 5 circle for the other, which is this guy. So if I take my 7 circle and my 5 circle and intersect them, that guy right there has a magic number of 2. And then you could find other points that have a magic number of 2. I'm so curious about this hypothesis. Can we ask, I'm going to clear all this stuff out and just try one more time. What if I want my magic difference to be 2? So for example, I just want to find the closest points to each other. So where would they be? So I want the difference to be 2. So, all right, so that's a 2. How far is it the rest of the way? Is that 5 more? Okay, so 5 minus 2 is 3. So, but I want my magic number to be 2. So I guess I got to go 1 more. Now, how far is it? So that's 3 here, and then how much is left? Is that 4 left? 4 and 3. So that's a magic difference of 1. So maybe I can't. Maybe the magic difference of 2, 1 is not. It's in between 2 circles. All right, I'm content to say magic difference of 1.
So, yeah, what would happen if you kept doing
Well, I mean, I think it must, so let's find it. So what we're saying, I guess, is that this point right here is on there, because if you do the blue distance, we get 3, and if we do the red distance, what do we get? The red distance here is 4. Okay, so I've got a 3, and I've got a 4, and when I subtract them, I get 1, and I just want to make sure that it's always 1. So there's another hyperbola there. That black dot is on that hyperbola. But let's go ahead and find that's like the closest, that's like the topmost one of the bottom branch. Let's find the bottommost point of the top branch. Where is it? Should be 3 away here, and 4 away from the other one is there. And so how far apart are those guys? One, you guys hypothesized that the green distance between them was the magic number. I'm getting closer to being convinced. Maybe that's our magic number, how close the hyperbolas are. Yeah, I guess that's it. I mean, it's the space, is that right? Space between. Yeah, what's left over? Yeah, I think we need to write the authorities here. Tell them we discovered something. Okay, good. Hypatia was a very smart person. Okay, and then our last of the conics, we did circle very briefly, ellipse, hyperbola, and then here's a parabola. Kyle? Okay, so there, like again, there's another formula for where the focus is, and you can look at it's in your book, I'm sure. But the idea, and you guys did this outside, you made your directrix like a curb, and then you found a point so that that distance going from the focus to the parabola was the same as the straight line distance between the parabola and the directrix. And then as you moved further up, maybe this distance here is bigger, but so is the straight line distance going down that way. And that's how we got to be on the parabola. Okay, so let's see if we can find the right web page this time. So we want drawing parabolas. Maybe this one. All right. Okay, so let's take a look. As we drag this thing, we got something that sure looks parabolic. Can we convince ourselves that in fact it is? Again, the definition is supposed to be that the distance between the focus and a random point on the parabola is supposed to be the same as this straight down distance. So Chris says yes. Are they the same? Let's close this guy here. So Chris, what are you seeing? Yeah.
However much is taken out is added to this.
Yeah, I think that's it. And I don't know why they picked yellow here. I can't make it anything other than what it is. But I think that's it. The you got your purple distance here is the space that's empty now, right? And then your blue distance is the string that we've taken out here. And they're the same because every time you move this thing, the string, like it leaves the blue and goes into purple, and it goes the same amount. It's just however long the string is, it's going to stay that same length. And so this one I can see a whole lot easier than the hyperbola one. Good. Okay, we can close that one, and I think I don't look at that. We're closing this one, and we're back here. Okay, number 6. We'll go to Vance. Okay, so what's the only difference between the ones we've studied and this other equation? Is that bxy part. So all the ones we've been doing didn't have an xy term. and it didn't, so that we could separate the x's from the y's and complete the square, just like you guys did on the quiz today. But it's quite possible it does have an xy term. I don't even know what that means in terms of trying to complete the square and make it look normal. But what the effect it has is that it kind of rotates the shape, so it's no longer like left-right, like our hyperbolas were perfectly left and right, or perfectly up and down. Well, now they could be off at an angle, up right and down left. That BXY is going to allow that kind of like angular type rotation. Okay, 7, Taciday. Delta. Okay, does that formula look familiar? What is that? It's called the discriminant of a quadratic equation. There must be some connection there. I don't know what it is. What's that? Nope, not at all connected. Everything's connected.
So is that implying you can't solve for an ellipse?
You can't solve for an ellipse? What do you mean?
In the quadratic formula, it's the square root of
It is, but it's not quite the same A, B, and C as in this equation, which is the one we're used to, right? The A is the A, but B is really D, which doesn't even appear in here. So it's like it is the discriminant with the same letters. What can I do? I don't make these decisions. Nobody consulted me when they. All right, so let's take a look at something. All right, so what if we just temporarily assume that B is 0, which is the thing we've been doing the whole time because we never had an XY term floating around. So if B is 0, then the only thing I care about here is this negative 4AC. And I said something the other day. I said if A and C have the same sign, then it's an ellipse. Okay, if A and C have the same sign, then what can you tell me about negative 4AC? It's going to be negative, right? Because A and C multiplied will be positive no matter what. So when I said A and B having the same sign makes, or A and C having the same sign makes it an ellipse, that, well, okay, it's true, but there's even more stuff. Like it's better than that. If A and C have opposite sign, then what can you say about this? It's a positive number, and if it's a positive number, it's a hyperbola. Wonderful. And if somehow, let's see, if A times Z, so we get a parabola sometimes. The only way to get a parabola is to make this 0. What must be true if this is equal to 0? It means one of them has to be 0, right? Either A is 0 or C is 0. Okay, so then we're really losing some terms. So we've already lost this. If I suppose for a second that C, let's suppose for a second that A is 0, then I'm looking at something like this. Let me suppose the other one, sorry. Suppose for a second that C is 0, and I'm looking at that equation. Is that a parabola? ax squared plus dx plus ey plus f. Like when you think parabola, you think y equals x squared. It is. And you think y equals x squared plus 5x. It is. That's exactly what this thing is. So okay, so all of the stuff we knew to be true before is still true, but somehow this generalizes it even further. And I made a GeoGebra thing yesterday, and this is the first time I've used it, so I hope it goes well. Okay, the A, B, C, D, E, and F in the equation that we were looking at is exactly the same as these letters up here. So at the moment, A and C are both 1. Lots of stuff is 0, and F is negative 1, which means if you move F to the other side, because F is assumed to be on the left, if you move it to the other side, it will become positive 1. So this guy is a 1x squared plus 1y squared equals 1. What is that the graph of? Circle. We knew it was a circle. You can check the discriminant, this b squared minus 4ac business. B squared, let's see, there's no xy term in that one, so that's nothing. 4 times a times c. 4 times the x squared guy times the y squared guy. Let's see what that is. There's the x squared guy, there's the y squared guy. 4 times those is 4. That's a negative in the front. It's negative, it's an ellipse. So now we're going to start changing stuff. So first thing I can change is f. If I change f, what happens? Circle just gets bigger. Super. What if, let's see, something's going to happen when I cross over this magic threshold. So here it's x squared plus y squared is 0.2. That's a small circle. That's a really small circle. X squared plus y squared equals 0. Can you tell me what points solve that? X and y must both be 0. Otherwise, you're going to get something positive. So it is a single dot. Smallest circle we could imagine. What if I try to make it x squared plus y squared is -1? It won't happen, not in the reals, right? And so the graph will disappear. There's nothing left. Okay, so that's fine. So we'll bring this back to -1. Now I'm going to start changing this a. Remember, a is the thing touching the x squared. So you can see the a is getting bigger, 2, 3x squared, 4x squared. What shape is that? It's an ellipse. It's weird. I thought by making the a bigger, I would make it bigger in the x direction. No, the radius is still, there's still kind of a 1 here, but let's see. So how much is the b squared? Remember, it's underneath the... That's what's going on. How much is your b squared, which is the guy underneath y squared? Is 1. So the up-down direction is still, up-down distance is still 1. How much is a squared? Well, I can't have a 4 there. I got to have something on the bottom. A 4 on the top is what on the bottom? Is a 1/4 on the bottom, right? A 4 upstairs, we need to write it as a 1/4 underneath. And now all of a sudden, square root of that is a half. My left-right distance is only a half now. So it's a little bit counterintuitive, but increasing the number in front of x squared actually decreases the left-right distance. Okay, so we got that. That's fine, and we can play the same game with the other guy here, the c. So I can increase this, and again, the same counterintuitive result. Okay, and then now you can see that there's this red line flying around here. That's delta, the b squared minus 4ac. I just calculated it here. It's -2.6. If delta is negative, what kind of a shape is it? It's an ellipse, and it is. But notice as I'm just going to keep kind of swinging this guy, make it smaller, 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 and at some point I'm going to make it negative, and all of a sudden that ellipse turned into what? Hyperbola. And like we kind of think of ellipses and hyperbolas as looking really drastically different, right? But this is a fairly smooth transition. I mean, it just kind of, like here it is. It's starting to say, I would really like to open up right and left. I'm just really trying to break through the chains. And there we go, we broke through. Yeah, it's a parabola. Let's see. So in this case, I think too many. Yeah. All right. Here's the equation that we're asking it to graph. It's it's 1.1 x squared equals 1. Because there's no y's anymore. I've gotten rid of. It's not even a two-dimensional thing anymore. It's just x's. Okay, 1.1 x squared equals 1. You can solve that. You'll find a single number for x that works, and they have graphed x equals that single number. But x equals a number is a vertical line. So if I really want it to be a parabola, I need to have the y. I need y's to still be in there. Okay, so let's just do our basic parabola equation. I know that my parabola, the parabola that I know and love, is y equals x squared. Okay, I'm not allowed to have anything other than 0 on the one side, so I'm going to rewrite that as an x squared minus y equals 0. Same? Okay, so how much is your capital A? That's got to be 1. B, 0. I don't have any x, y. C, 0. I don't have any y squared. D, 0. I don't have any x. E, -1. F, 0. Let's do that. So again, A was 1, E was -1, and F was nothing. Okay, A is 1, that's close enough. A is 1. What was it? D needed to be -1 and F needed to be 0. D needs to be, oh, E is -1? That's right, thank you. E, oh, look at that. E is -1 and F was 0. So there's our basic friend, the parabola, and you can see the red line right there is at 0. The delta is 0. But you can make other stuff where the delta is 0 by, I mean, like you got to be really careful. Like a parabola is quite a special thing. Like if I just randomly start moving stuff, I can just about guarantee you we're not going to find a parabola. What is that? Is it? The delta is negative. What is it? If the delta is negative? It's an ellipse. I can't see enough of it. Is it? Okay. It's an ellipse. But you could see that maybe, some of you didn't call it an ellipse. What did you call it? What is it close to? What does it look like? It might be. Maybe it's part of a hyperbola. Maybe it's part of a parabola. I mean, like you can see that like these conic sections, they look different, like kind of when you're zoomed in, but with this thing where there's unknown stuff off the page, I have a hard time even telling. Is it part of an ellipse? Is it part of a parabola? Is it part of a hyperbola? Shift the hyperbola, sure. We just need to make sure we have an xy term that exists. So if we want a hyperbola, so it could be x squared there. I'll make this guy negative. Oops. Make this guy -1, something like that. Is that what you wanted? So you can see that, I mean, like there's like endless room to play. Oh, something happened there. It's like they tag, you're it. So there's, that's kind of cool. It's a pretty subtle difference between the up, down, and left, right. What's that? Yeah. So anyway, there's lots of stuff to play around with here. We can make them with only violates the definition.
So I guess like, is there any way to get a parabola that is tilted?
Yeah. There's a parabola that's tilted. Whereas it's what? It's a parabola. Well, it's very close to a parabola. It's off by a tiny bit. I guess being off by a tiny bit means it's technically what? Technically, it's an ellipse. All right. I think if I want to really find it, I gotta hide this red line. Go away. So technically, it's just barely an ellipse, but it's trying to be a parabola. You can see, like, I'd be convinced, that's a parabola if ever I've seen one. I guess we gotta be really patient here. And whoa, what is going? Oh, what's going on there? Oh, it was an ellipse. How much was the D? I thought it was negative. Was it positive? Oh, if it was, I thought it was negative. Oh no, it is positive. It was just the y. It was the equal sign I was looking at. Uh-huh. Okay, so if the D is positive, what is it? It's a hyperbola. And I was convinced it was a parabola for the longest time, and then an ellipse, but there's the brother hanging out on the top left.
So. You're saying
you can. We just need to make something 0. So how can I make something 0? Let's go back here. So I need b squared minus 4ac to be 0. So just make up some numbers so that b squared minus 4ac is 0. That's the easiest way instead of playing around, because everything moves all the time. So we just need b squared minus 4ac to equal 0. So for example, if you pick and let's pick numbers that are between -5 and 5, because that's as far as my thing goes. But let's not pick the nicest numbers in the world, because I don't want to just see my standard parabola y equals x squared. So 2.5 for A, B is 4. Okay, that's fine. So let's see if we can find out what C is supposed to be. So we're doing 4 squared minus 4 times the 2.5 times C is supposed to equal 0. 16 minus 10C. Is that right? Is equal to 0. So C is 16 over 10, 1.6. Okay, let's try. 2.5. What's that? Okay. 2.5, 4, and 1.6. All right, 2.5 is there. What was the next one? Is 4? 4 there, and 1.6 was the last guy. 1.6. What's 4 point? Oh, should be 4. 4. Okay. Now I had really messed up my axes, so let's see if we can come back to reality here. But at least I see only one piece, so that's a good thing. Or what do you think, Garrett? Sideways parabola? How's that look?
So when you change the XY value, you're basically rotating with the parabolas.
I think that's a good way to say it. Yeah, it's a new axes system. Yeah. But I can't just change B right now because changing B will all of a sudden make it the wrong number for the A and the C. So if I change B at all, like you can see how picky parabolas are. I mean, like it wants to be an ellipse or it wants to be a hyperbola. It is only a parabola for this like one fleeting moment in time between the hyperbola and the ellipse. Now the nice thing is that the B squared minus 4AC formula does not have what letters? D, E, or F. So I can make D, E, and F anything, and in fact they were just kind of randomly left over for this guy, and it should stay a parabola. So what's it going to do? Let's see. So if I move D, looks like, oh my goodness. So I can make the thing, like the vertex is moving, it's getting shorter, all of a sudden it flips over completely. I can change E. I mean, it's a parabola the whole time. And then we can change F. This probably won't have as dramatic an impact because that's just the constant term. Yeah. Okay. If you would like to play with this, just ask me. I can email you this file, and GeoGebra is free software you can play with. All right. Number 8. Where are we for number 8? Kate. Okay, so let's take a look at this guy. If you have kidney stones and you need an operation to remove them, the operation for many, many years was an invasive one. They would cut you open and literally go in there and remove these kidney stones. But in recent years, we've come up with this advancement using this tool called a lithotripter. So the idea here, first to make sure we know what we're looking at, this is somebody lying on their back. This is their head, and we are looking at them from, right, they're going into the board and behind there, okay? That's the top of their head. And so we've got this lithotripter here. We take them, we lie them down in a certain spot. We know exactly where the kidney stone is. We've got like all kinds of ways to find that out without actually opening them up. We line them up in such a way that we've got the kidney stone at one focus of an ellipse, and at the other focus of the ellipse is this this device here. And so this thing right here is designed to be at the focus of the one ellipse, and the machine is just it's an ellipse, but it's a 3D thing. It's called an ellipsoid. But here's the idea. If you were to take like a flashlight and just shine it from the one focus anywhere onto the ellipse, it will bounce and exactly hit the other focus. This is the reflective property of the ellipse. Take a flashlight and shoot it, it will hit the other focus. And so what they do, well, they don't have a flashlight here. They have a little thing that emits sound waves. Now, sound waves are generally not, I'm emitting sound waves at the moment, and you guys are only hearing them, you're not feeling them. But if we have concentrated sound waves, then they will, sound waves are vibrations. And so they will vibrate whatever they hit. Now, this is not a lot of vibrating I'm doing to you, so you don't even feel it. But this is a very concentrated machine, and it sends out very, very strong sound waves. Now, if we were to just like shoot the sound waves like directly, like with a sound wave gun, directly at the guy and then through the guy into the kidney stone, that would hurt him. It would hurt all the stuff between like his outer layer of skin and then all the organs and things until it got to the kidney stone. So instead what we do is this. We take the sound waves, we don't shoot them in a straight line gun at the kidney stone, we shoot them in all different directions. And so, yes, the sound waves are all hitting his skin, and yes, they're all hitting the organs and stuff like that, but they're never concentrated like they would be if it was like a straight line beam. But they do get concentrated. Where do they get concentrated? At the other focus, which is precisely where the kidney stone is. What is it? That sounds good. So yeah, so like all of the power of these sound waves is focused. We use the word focus. I think this is why we use the word focus. It is focused. at the kidney stone. That's exactly where they put the kidney stone. And the kidney stone receives these vibrations, shakes a whole bunch, shatters into very small, little tiny things that can be passed non-invasively. Used to be like a 6-week recovery time from this. Now it's a few days. You know, what's that? I don't know what kind of frequencies. Bach. Yeah, you shouldn't move very much. Maybe, yeah, yeah. I have read that the sensation that the person feels on their skin is kind of like a rubber band, like somebody's like snapping a rubber band on your skin. So you feel it, but it's not, it's not painful or anything. But the kidney stone feels it quite a bit and shatters. All right, other places where ellipses come up. Well, right now we are orbiting the sun on an elliptical path. For a long, long time, people thought that the Earth was the center of the solar system and the sun revolved around it. Then, what's that? And it was flat. Then at some point, people started to realize that that did not jive with the observations they were making in the night sky. Some people discovered that the sun was actually at the center and we were revolving around it. It was assumed that we would revolve around it in a circle. What else is there? I mean, of course, like, and this was almost a religious thing. Like, all right, first we're going to put the earth at the center of the universe because God created the earth and all of us people. And so that's why we're at the center of the universe. He wouldn't do anything other than that. Okay, so that was a religious thing. All right, then we realized that that does not jive with what we see in the night sky. Okay, so fine, the sun is at the center of the universe, but it's a circle. God's going to create a circle. It's a perfect shape, round, everything symmetrical. And that did not jive. We needed much more precise observations to realize that it wasn't a circle. But eventually we had them, and somebody, do we know who, put it all together and realized it was an ellipse? Who was it? Galileo was a piece of this puzzle. No, it was a guy who had 3 laws, and one of those 3 laws, Newton did have 3 laws, but it was Kepler's laws of planetary motion, the first of which is that the planets revolve around the sun in an ellipse. And so I pulled up a couple of pictures here. Let's see if we can find those. So first, maybe that one is good. So the sun is here with the S, and Earth is out here with the E1, and we are rotating or revolving. I can never use the right word. We are going around the sun on that elliptical orbit. You can see that when we're closest to the sun, it's 91.5 million miles. And when we are farthest from the sun, it's 94.5 million miles. Okay, so that is 3 million miles difference. 3 million is usually a lot of whatever you're talking about. Relative to these numbers, is 3 million a lot? No, I mean, it's, maybe like 2.5% difference. Like, it's not that big of a difference, which means the ellipse that you are looking at here is really, really out of proportion. It is not nearly as elliptical as it looks. We are darn close to being a circle. It's just off a little bit. It's an ellipse. Oh, this is an estimate. This is rounded, I'm sure. I know we have far more accurate numbers than that one. It is. So I think it's center to center, center of the Earth to the center of the sun, and I'm sure we have a more accurate number than that. One thing, take a look. When are we closest to the sun? It's called perihelion. That happens on January the 2nd. In the dead of winter is when we are closest to the sun. For us, did God not create the northern hemisphere? Is that? So we are we are closest to the sun in the dead of winter for us, and we are farthest from the sun in the dead of summer, which is counterintuitive. The seasons have really, really nothing to do with how far we are from the sun. They have everything to do with the tilt of the axis. The Earth is not rotating around and revolving around the, like the polar stuff at a perfectly flush on to the sun. We are at a tilt. That is the sole reason for our seasons. And that's fine there. And if we come over here, close this. Okay, so I have not seen like a derivation for why our orbit is elliptical. I think that they are. I think pretty much it has to do with Newton's law of gravitational force and everything acting on everything. But I really think that because the sun is so much more massive than anything else near us, okay, sure, Pluto pulls us a little bit, and so does even Jupiter, but I really don't think that we feel much of it, if anything. There is a slight wobble, you know, you maybe hear that word talking about our path, but it's really, I mean, the sun pretty much dictates what we do.
Slowly adjusting to a circle, like if that's not much.
I don't know. I don't know. All right, we're closing, we're closing, we're closing. Here's something different. What else follows? So this is very tiny, but here are all the planets. What else follows elliptical paths is comets. And I don't know how many of you guys are old enough to remember Halley's Comet back in, was it mid-80s? Like 86? Yeah, 86. So Halley's Comet came by in 86. We knew exactly when it was going to come by because Halley's Comet follows an elliptical orbit, and it takes about 76 years. So 76 from 86, yeah, whatever that is, 2060-ish. So that's fine. So this is probably too small to see, but here's another one. Okay, here's another one. Comet Hyakutake, which takes roughly 17,000 years to make one elliptical orbit. I don't know.
Yeah.
Check. What time is it? 20 minutes. Okay, last thing. So that's the elliptical stuff. Parabolas are probably the most important conic for us on a day-to-day basis. There are a lot of things that are parabolic in this world. For example, if you have a flashlight, it is a tiny little bulb, but it produces a concentrated beam of light in front of you because there are mirrors inside of that flashlight. And the mirror is actually shaped as a parabola, a 3D parabola. And the radar dishes too, because in a parabola, everything reflects straight out that comes from the focus. So we put the little flashlight bulb at the focus, and then it's a concentrated beam of light. Same thing with your car headlights. It's not that big of a light in there, but it comes out as a straight focused concentrated beam because of this parabola thing. If you look at satellite dishes, you will see giant 3D parabolas because the satellite dish is trying to catch all of this wonderful cable signal from the sky. If it was just a guy out there holding this little kind of receiver, it wouldn't catch very much. So we put this enormous parabola shaped thing so that any signal that comes into the parabola is caught and then sent right to the focus, which is exactly where we put that receiver. Same thing on the NFL sidelines, like there's a little guy holding a microphone with a parabolic dish so you can get the sounds of the game. And you will hear what's happening 50 yards away because all the sound coming in, barely any of it hits the microphone directly, but all of it hitting this big dish will get reflected to the microphone. All right, parabolas and you. Sorry for going over, and we'll see you guys on Monday.